Hello everyone, Simon here. Let's continue learning about the brain and learning about psychology with Google Gemini, the AI. Okay, so last time we talked about neurons, right? Let's go and take a more macro view and look at the brain as a whole, right? What I'm going to say to Gemini, I'm going to say, let's let's switch to a macro view of the brain. You mentioned earlier that the brain is modular, that different parts have different functions. Can you, can you, hmm, describe the different parts of the brain in a way that is easy for lay people to understand. So there's a concept called the triune brain. It's kind of been disproven in some ways, but the underlying division of the brain into three areas is kind of useful. I don't know if I should like ask Gemini to do that or just let it decide for itself. Can you describe the different parts of the brain in a way that is easy for lay people to understand? Perhaps begin with the autonomic functions, then moving on to emotions and then cognition. All right, let's see how Gemini replies. Yeah, so triune brain, there's problems with the idea of the triune brain, but let's see what Gemini says, right? I'm using fast. I want to use thinking. Can I redo this? I'm gonna redo this. Why is it going too fast? Can I? Huh. I guess I don't get to use thinking. Why don't I get to use thinking? Alright, I'm going to use thinking. Yeah, no, we don't want the fast. The fast response is not great. So, Gemini says, a great way to visualize the brain structure is to think of it like a three-story house. Each floor is built at a different stage of evolution. Yeah, that's not entirely true. Anyway, the bottom floor handles the basics of staying alive, the middle floor handles how we feel, and the top floor handles who we are. Right, so level 1, the basement, the brainstem and the cerebellum. I don't know if the brainstem is here. Oh, brainstem, there it is. The brainstem, is that thing down there? Well, that's part of it. Hold on, can I go back? Brainstem, let's get the whole brainstem. Alright, brainstem is that thing down there. That's the thing that connects to your spine. Right, so the nerves go down to your spine there. That's the brainstem. And the cerebellum is that thing down there. So also like at the bottom of the brain. So the brainstem and the cerebellum, they're at the bottom of the brain. Like at the, back here and underneath everything else. The function is autonomic and survival. These are the oldest parts of the brain. They work automatically. You don't have to think to make them happen. If this level is damaged, life becomes very difficult to sustain without machines. Right. So when it says these are the oldest part of the brain, Gemini means they're evolutionarily old. So the origins of the brainstem goes all the way back to worms, right? Worms have similar structures, and then all animals have the similar structures, or analogous structures, should we say, to the brainstem. Um, so they control automatic things in your body, so like your heartbeat, your digestion, things you don't think about, things that just happens automatically. And if it gets damaged, as Gemini says, like your heart stops beating and then you die, right? So like all the basic biological functions that your brain controls, but which you don't have to think about. So there's the medulla and pons. This is your autopilot. It controls breathing, heart rate, and blood pressure. It's why you don't stop breathing when you fall asleep, right? So things like breathing and heart rate. Medulla and pons. So there's the pons, by the way. Can I like get in there? So there's the brainstem, there's the pons, and then the medulla is, if I can, nope. Where's the medulla? Medulla oblongata. Right, so it's down there. So the medulla is that one, and then the pons is, oh, I can't see it. The pons is that one. Why can't I click on it? Right, the medulla and the pons there. And then the cerebellum located at the back. This is the autocorrect for your movements. It coordinates balance and fine motor skills. When you learn muscle memory, like riding a bike, you are training your cerebellum. I'm not sure that's entirely accurate. The cerebellum does a lot of different things. That is one of the things that it does. But the cerebellum, I believe it also does other things. It doesn't say there what it does. So the way we know how this stuff works is if it's damaged, like if somebody's cerebellum is damaged either in an accident or a disease or brain tumor or whatever, then people lose their ability to do fine motor skills. But that doesn't mean that's the only thing that it does, the cerebellum. It I think it's used for other learning tasks as well. But anyway, that's one of the things that it does. The thalamus thinks of this as the grand central station. Almost all sensory information except smell stops here first before being routed to the higher floors. So the thalamus is that there. So that is part of the brain stem apparently. But all your senses come to here, except smell, come into here before it's routed to your cerebral cortex. So it routes the signals to the rest of the brain from your senses. Right, so that's the brainstem part, the brainstem and the cerebellum. And then level 2, the living room, the limbic system. Function is emotions and memory. Oh, there you go. The limbic system is, so the brainstem is this stuff down here, brainstem, cerebellum. The limbic system is above and inside the cerebral cortex. This is where life gets colored with meaning. This system decides what is important, what is scary, and what is worth remembering. So this is your emotions and your memory, or your emotional memories. So there's the amygdala, the smoke detector. I don't know if we want to use these analogies. It's kind of weird. The amygdala, this tiny almond-shaped part, scans for threats. It triggers the fight or flight response. In Phineas Gage, his amygdala was still working, but he lost the ability to control the signals it sent. So the amygdala is there, that little thing there. And this is the one that either gets angry or it gets scared. The hippocampus, this is responsible for forming new memories. It doesn't store the books, but it indexes them so you can find them later. the hippocampus. Cerebral cortex, hippocampus is that thing there. So it like it's part of the memory system, especially the emotional memory system. So it basically like it ties your emotions to certain memories. That's the hippocampus. The hypothalamus, it regulates your internal state, hunger, thirst, body temperature, and sex drive. It is the bridge between your brain and your hormones. Right, the hypothalamus. The hypothalamus is that thing there, right there in the middle there. There are other parts of the limbic system as well. We're getting kind of simplistic here. That's okay. And then we get to the top, the penthouse, the cerebral cortex. Cerebral cortex is the big thing here, right? The function is cognition and the human experience. This is the wrinkled outer layer that makes us uniquely human. It is divided into four main lobes, each with a specific department. The occipital lobe at the back, the visual processor. It takes the raw data from your eyes and turns it into seeing. I mean, sure, it processes visual data basically. The temporal lobes, the sides, the auditory center. It handles hearing and is crucial for understanding language. Hold on, let me just zoom out. So the occipital lobe is there. The temporal lobe is there, although as you can see in this model, there's more stuff than what Gemini is talking about. But the temporal lobe is there. The parietal lobe, top and middle, the data integrator, it handles touch and spatial awareness, helping you know where your limbs are without looking at them. So this is sometimes called the motor cortex. This stuff. So touch and movement. The frontal lobe, the CEO, this is the most human part. It handles executive functions, planning, decision-making, personality, and criticality, and critically impulse control. So this is the part that thinks. Up front here, this stuff, well, this stuff is the part that thinks logically and rationally and purposefully, right? We don't need the summary, and we don't really need the Phineas gauge connection either. So I want to like dive deeper actually. Can you go into further detail? Can you go into further detail? Can you describe, explain the brainstem and cerebellum in further detail? I just want Gemini to elaborate more. So this is like a very basic outline. So there's the autonomous part, the emotion part, and then the thinking part. Right? If the cerebral cortex is the sophisticated software of the brainstem and cerebellum are the hard-coded hardware. I don't know if that's true. I mean, the brainstem more so than the cerebellum, maybe. They're the essential foundation. Without them, there's no you to speak of because there would be no heartbeat, no breath, and no movements. Right, the brainstem, the gateway of life. The brainstem is a small, stalk-like structure at the very base of the brain. It's not that small. It is the most critical real estate in your body because it is where the brain and the spinal cord meet. Right? It is divided into three main sections, moving from bottom to top. The medulla oblongata, the vital core. This is the lowest part of the brainstem. It handles the things you must do to stay alive, but never want to think about. Life support, it regulates heart rate, blood pressure, and breathing. The reflex center, so this is some of the detail that was missing before, right? It controls protective reflexes like sneezing, coughing, swallowing, and vomiting. So like if you feel like you're choking, you would gag, or like if you get irritated, you would sneeze, or if you feel something is stuck, you'll cough. So so reflexes like that is to save your life, and it happens automatically. And then there's the crossover. Interestingly, the medulla is where most of the nerves from the left side of your body cross over to the right side of your brain, and vice versa. Right. So like it doesn't actually like it doesn't only handle the autonomous function, although that's some of the most important things that it does is the autonomous functions. But as it says here, the two halves of your brain, the signals cross over through the medulla, right? And so it's not just connecting the brain to the brainstem, it's also connecting different parts of the brains together. So connecting the left side and the right side of the brain together. So when you're thinking, like all the signals will go through the medulla as well. Um, so it's not just controlling the body functions, but also coordinating all the communications between the different parts of the brain. All right, B, the pons, the bridge. Pons is Latin for bridge. It sits just above the medulla and serves as a massive relay station. Communication. It connects the higher brain cortex to the lower brain cerebellum. I think cerebellum is used for a lot of different things. Uh, like sometimes your brain will send signals to the cerebellum and get signals back. Sleep and dreams. The pons play a key role in generating the paralysis you experience during REM sleep, so you don't physically act out your dreams. I think it does more than that. But one of the things that it does is that when you're dreaming, it stops the signals from going down your spinal column, right? Because when you're kind of moving around, when I'm moving around, like the signal kind of goes down through the spinal column and then to my arms, and then I move my arms around, right? So when you're sleeping and dreaming, the pons will cut off that communication, does not send the signals down your spinal column, so you don't move around so much when you sleep. Although sometimes when you're dreaming, you still move around a little bit. And then with the midbrain, the sensory scalp, the smallest and topmost part of the brainstem. It deals with reflexive seeing and hearing. If a loud bang happens behind you and you instantly whip your head around, that's your midbrain. It handles basic visual and auditory reflexes before your thinking brain even knows what happened. Fascinating. So this is the faster part, right? If something flashes and you look at it, that's the part. Like the midbrain is where that happens. Before it goes to the visual cortex for you to even process what that signal is, you've already reacted to it. So this is the fast part of your visual and auditory reflexes. It's also the dimmer switch, the reticular formation. Running through the center of the brainstem is a web of neurons called the reticular formation. It acts like a dimmer switch for your consciousness. If it's turned up, you are alert and awake. If it's turned down, you are asleep or in a coma. It filters out background noise like the hum of an air conditioner, so your higher brain can focus on what matters. Alright, so this is the part that lets you sleep. It it filters out things that it's not important. So you only send the important signals to your cerebral cortex, right? So it kind of it regulates basically. It regulates the input and output into and out of your brain. And then there's the cerebellum at the back of the brain. Located at the very back of your skull, the cerebellum looks like a mini version of the whole brain. While it only takes up 10% of the brain's volume, it contains more than 50% of all the neurons in your entire head. Yeah, so the cerebellum is super interesting. We don't know for sure what it does, but it contains a lot of neurons, and it might actually do a lot of the thinking. Um, let's see what Gemini says, right? The master of coordination. If your frontal lobe says, I want to pick up that cup of coffee, the cerebellum is the one that calculates exactly which muscles need to fire, in what order, and with how much force. Isn't that interesting? So you make the decision, and the cerebellum figures out how to move your muscles to do that thing. Error correction. The cerebellum is a prediction machine. It compares what you intend to do with what is actually happening. If you trip while walking, your cerebellum detects the imbalance in milliseconds and sends corrective signals to your muscles to catch you. So interesting. The cerebellum is one of the most interesting things in the brain, I think, from a functional perspective. Procedural memory. This is where muscle memory lives. When you play a guitar or type on a keyboard without looking, your cerebellum is running those learned patterns. So it's like a dedicated information processing, or like a dedicated learning part of the brain, if that makes sense. Um, I mean, you know, at the risk of being too simplistic, I think it's like the GPU in your brain. Like this is the part of the brain that does a lot of the parallel calculations, I think. Because for example, like trying to figure out, for example, like you want to pick up the coffee, and then you have to figure out how to move your muscles to get the coffee. Like it's those calculations that the cerebellum does. The new discovery, the cognitive cerebellum. For a long time, we thought the cerebellum only handled movements. However, recent neuroscience shows it also helps smooth out our thoughts and emotions, just like it smooths out our walking. It helps with timing, estimating how much time has passed, language, finding the right word in a conversation, emotional regulation, helping to break sudden bursts of anger or sadness. Right? The cerebellum is very important. It does a lot of things, and we're still not entirely sure all the things that it does. All right, so that's the brainstem and the cerebellum. Slightly better, slightly more detail. I appreciate that. Um, let's go. I wonder if I should ask more detail here. No, let's move on. All right, now let's next. Can you describe and explain the limbic system? I mean, it did call it the limbic system, right? Yeah, the limbic system in more detail. In more detail, there are a lot of small parts. From what there are a lot of small parts here. And they all handle different emotions. I don't know if I'm right or not. I think that's how it works. The limbic system is often called the mammalian brain because it became highly developed in early mammals to help them navigate social groups, remember where food was, and avoid predators. So this is your emotions and your instincts. In our three-story house analogy, this is the living room. This is where raw survival instincts from the basement are turned into complex feelings and memories. While it is made of many small parts, they all work together to answer one question. Does this matter to me? Hmm. Right, the amygdala, the emotional smoke detector. Basically, by smoke detector, it means like, are you in danger? This tiny almond-shaped structure is the brain's alarm system. Its primary job is to scan the environment for salience, things that are important or threatening. Right. So it's looking for things that are important. Fear and aggression. When you see a shadow in a dark alley, the amygdala fires before your conscious brain even knows what it's looking at. It triggers the fight or flight response, which is amazing, right? If you see like how small it is, this is the amygdala, it's tiny. It is tiny. But somehow, when you see something that you might be scared of, like it immediately triggers, even before you can think about it. So it's very small, but it's very effective, right? Emotional tagging, it tags memories with emotion, well, especially like negative emotions, fear and aggression emotions. If you were bitten by a dog as a child, the amygdala ensures that memory is vivid, so you remain cautious around dogs in the future. So, like you have memories, and each memory often, usually, is tied to an emotion. And so then from that point onwards, you get PTSD basically. Every time you see a dog, you remember being bitten and you get PTSD. If you're wondering why do I have PTSD? It's because of your amygdala. PTSD, if you don't know, is post-traumatic stress disorder. So you experience a trauma, that trauma get associated with those feelings of fear, and then next time you experience something kind of similar, it triggers the fear again. And so that's this. That's what this is doing. It tags the memories with the emotions of fear. And so then when you see similar things, you feel the fear again. Like the fear and the memory becomes tied together. Alright, next part, the hippocampus, the librarian. Named after the Greek word for seahorse because of its shape, the hippocampus is the center of memory and navigation. The hippocampus is this thing. Memory consolidation. It doesn't store memories permanently. Those eventually move to the cortex, but it converts short-term experiences into long-term memories. The emotional glue. The hippocampus and amygdala are neighbors for a reason. Emotion is the glue that makes memories stick. This is why you remember exactly where you were during a major world event, but can't remember what you had for lunch Tuesday. Right. So, more emotionally intense memories, they stick longer. Spatial awareness, it helps you create a mental map of your surroundings. Very interesting. And then the hypothalamus, the master regulator. Though only the size of a pea, the hypothalamus is arguably the most busy part of the limbic system. It maintains homeostasis, balance. So the hypothalamus, that thing. The four Fs. Evolutionary psychologists often joke that the hypothalamus controls the four Fs: fighting, fleeing, feeding, and fornicating. Hmm. And if you think of like a more simple animal than us, like like a simple mammal, that's basically all they need to do, right? To survive, and then to reproduce. So like this is the basic functions of an animal, is those things. The brain-body bridge, it tells the pituitary gland to release hormones. It is the reason your heart races when you're nervous and why you feel butterflies in your stomach. Right. So, right. Controls hormones? The cingulate gyrus, the emotional buffer. This is a fold of tissue that sits right above the rest of the limbic system. It acts as a bridge between the emotional living room and the rational penthouse. Conflict monitoring, it helps you switch your attention between the different tasks. Emotional regulation, it helps smooth out the raw signals coming from the amygdala. When you're angry but choose not to scream, your cingulate gyrus is working hard to mediate that conflict. Well, yeah, I guess. So this is the communications, right? So the emotions come from here, and they send signals to your cerebral cortex for your brain to try to figure out what to do about those emotions, right? You have to think about what you're going to do. And then once you've thought about it, it sends signals back, and then if you want to act on it, it goes down the brainstem, right? So the singular gyrus is basically the connections between the limbic system and the cerebral cortex. But they're not just connections, it does do some processing as well. So that's the limbic system. I mean, there's a lot of stuff in there that we skipped over, right? Anyway, let's move on. Oh, wait, a note on the reward center. There is one more small part often associated with the system called the nucleus accumbens. This is the brain's pleasure center. When you eat chocolate, win a bet, or get a like on social media, This area floods with dopamine. It's the part of the limbic system that drives addiction and wanting. So the nucleus accumbens is not on that diagram. What's it called again? How do you spell it? It's there. So the dopamine comes from there. So pleasure is there, and then the fear is there. Fear and anger and pleasure. So there are like different parts that generate different feelings. And that's your limbic system. All right, so move on to next. Please give us a more detailed breakdown of the cerebral cortex. Make sure to cover all the parts. There's a lot of parts. Make sure to cover all the parts, different parts. So when you look at it, it looks kind of undifferentiated, right? The cerebral cortex from the outside, I mean, it looks kind of undifferentiated, but actually it is folded into different parts and they all do different things. Welcome to the penthouse. The cerebral cortex is the thin, wrinkled outer layer of the brain that makes up 80% of its total mass. If you unfolded it, it would be about the size of a large dinner napkin. But because it's folded into all those little hills, gyri, and valleys, sochi, soci? I think it's sochi. It fits inside your skull. This is the seat of complex thought, language, and consciousness. It is divided into two hemispheres, left and right, connected by a massive bundle of fibers called the corpus callosum. The hallway connecting the rooms. Each hemisphere is divided into 4 distinct lobes, each with its own specialized department. Right, the frontal lobe, the executive suite, located right behind your forehead, right there. This is the most recently evolved part of the human brain. So this is recently evolved is it's more complex than that. So if you look back at our evolutionary history, the prefrontal the frontal lobe, it's always been there. It just hasn't been very big, right? So as we evolved and as humans became smarter and smarter, the frontal cortex got bigger and bigger. And so that's what Gemini means when it says it's most recently evolved is, it's the part that got bigger, latest. But that doesn't mean it wasn't there before. There was always, a part of a part of the brain that you would identify, oh, that would later on become the frontal cortex. So you can see it even in more primitive animals, but they don't use it very much and it's not very big. So when it says most recently evolved, it doesn't mean that primitive animals don't have a frontal cortex. They do have a frontal cortex. It's just that it's not as developed, right? Like the most recent evolution of humans saw the frontal lobe increasing in complexity much more than the other parts, is what Gemini actually means. So there's a bit of a nuance there. The prefrontal cortex, this is the CEO we've discussed in Phineas Gage's story. It handles decision making, planning, and impulse control. So this is if you want to know where your consciousness is, like where you make conscious decisions, this is the conscious decision making part of your brain, right there, right in front. The motor cortex, a strip at the very back of the frontal lobe that controls voluntary muscle movements. Your right motor cortex controls your left side, your left hand, and vice versa. Left side, actually, and vice versa. So the motor cortex is, I guess there. It says premotor cortex. Is it further back? Precentral gyrus? Nope, it's like back there. Is it inside? Why can't I? Nope, never mind. Cerebral primary motor cortex. Oh, it is here. It is that one. Alright, so the motor cortex is that one. There. So you know, like your prefrontal cortex decides to do something, and then the signal goes to your motor cortex to actually execute the action, and then that communicates with your cerebellum to figure out how to move, and then it goes down your brainstem into your body to move. So you see like the different parts of your brain, the signals go from one to the other, you make a decision, you decide to move, you figure out how to move, and then you actually move. Broca's area, usually in the left hemisphere. This is the speech production center. If this is damaged, you might know what you want to say, but physically can't form the words. Fascinating. Can we? Left side. It is this side. I wonder if we can find it here. Broca's area? Oh, it's right there. It's near the front, huh? Broca's area, that's the part that handles speech, although it's also on the right-hand side. So if you damage one or the other, I think it says usually the left-hand side. So if you damage the left-hand side, you forget how to speak. You might be able to train the right-hand side one to learn to speak again, maybe. And then the parietal lobe, the command center for sensation. Located at the top and back of the head, it is responsible for processing sensory information and helping you navigate space. This one. So you notice the motor cortex? It overlaps, right? The motor cortex is there, so like your physical senses is there, and then your movement is there. So your body, so you kind of tell your body to move, but then you get sensory input from your body as well. So the brain is laid out so that things that are related to each other are put next to each other, right? So you make decisions here, and then you speak there. So you have thoughts, and you verbalize your thoughts, right? So that like it's closer together because they work together. Located at the top and the back of the head, is responsible for processing sensory information and helping you navigate space. The somatosensory cortex. This strip sits right behind the motor cortex. It processes touch, pressure, temperature, and pain. So all the things that you experience on your skin, that is right next to your motor cortex. So like if you move and you touch something, like it's like all the signals are right there in that general area. Spatial mapping, it tells you where your body parts are in relation to each other. It's why you can touch your nose with your eyes closed. So it remembers where your different body parts are. And then the homunculus, if you map the body onto these strips, you'd get a little man, the homunculus, with giant hands and lips, because these are the areas with the most because those areas are the most sensitive and require the most brain power. So here's a diagram of the homunculus. So it's that little strip there, in there. And if you map the brain to your body parts, so the parts of your body that has more nerve endings, it takes up a bigger part of the brain. And then the parts with fewer nerve endings, it takes up a smaller part of the brain, right? Right, so that's what's that? The parietal lobe, and then there's a temporal lobe. Oh, there it is. The brain's flipped around, so this is the right side. Broca's area, prefrontal cortex, primary motor cortex, auditory cortex, Wernicke's area, angular gyrus, visual cortex. It doesn't label everything though. The temporal lobe is the sound and meaning studio, located near your temples, behind your ears. It handles hearing and is deep-seated in memory. So right next to your ears is the part that handles hearing. and also memories. The auditory cortex processes sounds from your ears. The Wernicke's area, usually in the left hemisphere, this is the language comprehension center. If Broca's area is for speaking, Wernicke's is for understanding. Damage here leads to word salad, fluent speech that makes absolutely no sense. Fascinating. Fascinating. So this is the part that figures out what words mean. And then object recognition helps you recognize faces and objects, a specific part called the fusiform face area. It's what allows you to recognize your mother's face versus a stranger's. And then behind that, the occipital lobe, the visual projector. The occipital lobe is that part at the very back. Located at the very back of the head, it has one primary job, vision. Primary visual cortex. It receives raw electrical signals from your eyes and begins to interpret them into shapes, colors, and motions. Fun fact, this is why seeing stars happens when you hit the back of your head. You're physically jarring the neurons in your visual center. Don't do that for fun. That's not fun. It's not fun about it's nothing fun about brain damage. Uh, Integration, the connectome. While we talk about these as separate rooms, no lobe works in isolation. For example, to read the sentence, your occipital lobe sees the shapes of the letters. Your parietal lobe helps track where you are on the page. Your temporal lobe, Wernicke's, deciphers the meaning of the words. Your frontal lobe decides whether to keep reading or check your phone. The Phineas Gage postmortem. Now that you see the whole map, you can see why Gage was such a specific miracle. The rod entered through the cheek and exited the top front of the head. It completely bypassed the occipital vision, the temporal language hearing, and the parietal sensation movement. So all the parts that control the body and interprets the senses were intact. It specifically targeted the executive office, the prefrontal cortex. This is why he could still see, talk, and walk, but his human operating system was corrupted. Right? Very cool. Neuroplasticity, the amazing way these four lobes can actually change their shape and function based on experiences. So I'm not going to ask about that, but just to kind of talk about it. So like blind people will have a smaller occipital lobe, and then the other parts would kind of just take over those functions. So what I mean is like the brain would stop being part of the occipital lobe, and it will like the hearing part and the sensory, like the touching part, would grow in size to take over that space, that the unused space. So that's neuroplasticity. So like a blind person who doesn't get any visual input, the brain would like repurpose those neurons. So like blind people can hear more precisely than people who are not blind. And they can they can feel things more precisely than people who are not blind because their brain has been repurposed, right? The part of the brain that would be used for vision in people who can see, that part is repurposed. So that's for example, that's neuroplasticity. Your brain is not static, it can grow and change. So those are the different parts of the brain. And at the end there, it does talk about how like when you're reading text, for example, it engages the different parts of the brain in sequence. I wonder if I should ask more about that now. Mm, or later, because I do want to. I will be asking more about this stuff later. Maybe I do that later. Um, what's a good question to ask here? I want to ask. What I want to ask about is, like for example, when you do something, and like all the different parts of the brain work together to figure the thing out, right? What's a good example? let's say you cross the street. Right, let's say you cross the street. Now that we've had an overview of the different parts of the brain, can you perhaps give us some examples of how the brain handles doing some everyday things, as in the parts of the brain activating and coordinating with each other to produce, to make actions, to make decisions and take actions. Maybe I wonder if Gemini can actually do this. For example, what happens when a person crosses a street and they have to check they are safe before they cross? Let's see if Gemini can handle this. I don't know if it can. Crossing the street seems like a mundane task, but for your brain, it's a high-stakes symphony of electrical and chemical signals. It requires every floor of our three-story house to work in perfect synchronization. I mean, that's why I asked, right? Here's a step-by-step neural breakdown of a person standing at a busy intersection. Right, phase 1, the goal, frontal lobe. Before you even look at the traffic, your prefrontal cortex, since the CEO, sets the intention. It holds the working memory of where you are going. For example, I need to get to the grocery store on the other side. It initiates the sequence of actions required to achieve that goal. Right, phase 2, the data sweep, the occipital, temporal, and parietal lobes. As you reach the curb, your sensory suite goes into overdrive. The occipital lobe processes the color of the traffic light and the speed of oncoming cars. The temporal lobe listens for the hum of an electric car you might not see or the chirping sound of the pedestrian signal. The parietal lobe integrates this information to tell you exactly how far away the curb is and where your body is positioned in space. And in phase 3, the risk assessment, the limbic system. This is where the living room weighs in, the amygdala. If a bus zooms by too close, your amygdala flashes a danger signal. This triggers the hypothalamus to release a tiny burst of adrenaline, making you more alert. The hippocampus quickly checks your files to remind you that this particular street is usually busy and you should wait for a complete stop. Right, phase 4, the go, no-go decision. The prefrontal cortex again. So the prefrontal cortex decides to cross the street, and then it brings in all this information from the sensory parts and also your emotions. Now comes the most critical part, the one Phineas Gage struggled with. Your brain sees a small gap in the traffic. The limbic system might say, I'm in a hurry, let's run for it. The prefrontal cortex, the brake, calculates the speed of the approaching car and inhibits the impulsive urge. It decides, no, that car is moving too fast, we wait. Right, so there's like competing signals in your brain, and your prefrontal cortex has to figure out which one is the correct one, right? Like you might want to cross, or you might say, oh, that's too dangerous. And you have to figure out, like, you can see the car, you have to figure out how fast it's going, and so then your prefrontal cortex decides, oh, is it too fast? Is it too soon? Do I have enough time? And in phase 5, moving out, motor cortex and cerebellum. The light turns green, the CEO sends the go command. The motor cortex sends a signal down the spinal cord to your leg muscles. The cerebellum, this is the gyroscope. It ensures that as you step off the curb, you don't trip. It adjusts your balance in real time if the pavement is uneven. And then the basal ganglia. This group of structures deep in the brain helps smooth out the start of your walk so you don't move like a robot. And then phase 6, the autopilot, the brainstem. While all this complex decision making is happening, your brainstem is quietly working in the basement. It ensures your heart rate stays steady and you keep breathing, even if you're holding your breath in anticipation of the traffic. Oh, very cool. Very, very cool. That's pretty good. I like that. So this is like a, very simple, um, like example of, when you're trying to do something, like different parts of your brain do different things, and they all coordinate together to figure out what to do and how to do it, and then to actually do it. Very, very cool. Okay, so I'm gonna end this here. So we looked at the different parts of the brain, and we looked a little bit at how they work together, right? Mm. So next time I want to talk about what happens like when you feel things, or think things, or do things. So kind of like the crossing the street example, but just more examples and in more details, right? And I think I want to talk about like actual emotions. But okay, I'll see you next time. We'll get to it when we get to it. Next time, let's talk about specific emotions and how your brain triggers and then reacts to those emotions. I'll see you next time.